All right, we're on for lecture 29, which is the last lecture. And so I just want to sort of clean things up and make a couple of points. Throughout the course, I've been trying to emphasize that the essence of this material is not simply calculating formulas. In fact, that's kind of distracting. The essence is understanding what's going on and recognizing that the results that you get are sometimes intuitive, sometimes counterintuitive, and it's the fact that on the one hand this stuff seems so easy, on the other hand it's so hard sometimes that interaction of those things is, to me, what makes the subject interesting. And what I was talking about was the MG1Q and then the MG1Q with vacations. So let me briefly say where we are and then look at some of the consequences of having vacations. So in ordinary MG1, we talked about the embedded Markov chain. So that's an important concept. The idea is that by looking at the Q the right way, that is, by looking at it from the viewpoint of service completion epochs, the number left behind by a departure at a service completion epochs, that allows us to write and solve some equations. At first glance, that looks like it's not enough information because it tells you what people leave behind, not what they find. But somehow it all works out because of the Pasta theorem and Little's theorem. So the basic idea is that we say that the probability that a departing customer, that's what the star is, leaves behind J. We relate that to the probabilities for the customer who left just prior to him. So the previous customer could have left behind 0, and in which case the next departure will leave behind J if exactly J new arrivals occur during his service time, because if this guy leaves behind 0, the next guy must find 0, and then what he leaves behind are all those that arrived during his service time. And the probability that J arrived during his service time, we call that little pj. Then there's the probability that the preceding customer left behind I, where I is now lies between 1 and J plus 1. The 0th case we've already taken care of, and the J plus first case, well, you can't go higher than J plus 1 because you can't leave behind more than one customer than what it is you found. In other words, if I leave behind 10, the least that the guy who arrives after me can leave behind is 9. Okay, so then if this guy leaves behind I, this guy will leave behind J if during the last service time the number of arrivals was J minus I plus 1. And we solved these equations and we got the this G of Z. So G of Z, by definition, was the generating function of these pi j stars. And the G of Z contains the little p's, and the little p's is where the service time distribution function is contained. Okay, then if we looked at the MG1 with vacations, even though that looks like it's much more complicated, it turns out that if you take the right viewpoint, the equations that describe it are almost the same. So now, let's call those things pi j star with a hat. So the hat refers to the vacations. And now you could say that, well, let's look at these two kinds of terms. First of all, suppose that the preceding departure did not leave the system empty. In that case, the probability that the next departure will leave behind J is exactly the same form as the expression right here. So I'll write that out. That would be the sum. Let's see if I got erase this better, too greasy. Okay, we have the sum as I runs from 1 to J plus 1. Maybe a new marker will work. of P, obviously not. Try one of these. Obviously, this is the toughest thing about this course, is being able to write stuff on this board. P, j minus I plus 1, pi hat I sub star. So this term is just like this term, except it has hats over it because it applies to the vacation model. And the only difference is in this term right here. This is where the vacations come in. So you say that in this case, let me write this down and then explain what the terms are again. Okay, so if the previous customer left the system empty, then what that means is the server goes on vacation. When the server returns, it finds a certain number of customers there. If that number is 0, then it goes on a vacation again, and it keeps on doing that until it finds at least 1. And when it finds at least 1, then it stops and it serves all of those customers and all of their descendants before it goes on a vacation again. So I could define P sub I, capital P sub I. That's the probability that when the server returns from a vacation, it finds I customers. But it only stops if I is at least 1. So I'll divide that by 1 minus P0. So this gives me this term now that I'm writing. This is now the probability that when the server returns from vacation, he finds I customers where I is more than 0. So that means he doesn't go on another vacation, he starts to serve. And when he serves, the probability that the number that he leaves behind is probability that the next guy leaves behind J is the probability that during that service time, exactly J minus I, let's see, I need more room here. Let me write this out so I have more room. This is the sum. I'm just recopying the last term. I runs from 1 to J plus 1, little p, J minus I plus 1, pi hat I star. Okay, now, the server goes on vacation, returns from vacation. This is the probability that when he does, he finds exactly I waiting. And then, if in fact the previous customer had left the system empty, that's what makes the server go on vacation, then if during that service time, exactly J minus I plus 1 new customers arrive, where I then is summed just like before from 1 to J plus 1, then the next departure will leave behind J. So the point is that if you is understanding this embedded chain, set of embedded chain equations, and then when you solve them, recognizing that this is the same as that, and in fact, this is almost the same as that as well, because if I just factor out the pi I 0 star and the 1 minus P0, then this term here looks exactly like this term, except that instead of having the generating function of the little p's, it's going to contain in it the generating function of these p's. Okay, so the bottom line is that when I get done, I get the following result. Okay, so now what I'm doing is I'm looking at where you're asked in exercise number 12 on page 222 to do all this stuff. And what you're supposed to show is that the generating function that you get, the hat now corresponds to the generating function for the vacation probabilities. That's given by the following form. It's f of z minus 1 divided by f prime of 1 times z minus 1 times g of z. In other words, what comes out of all of this is that the generating function of the number of customers left behind by a departure in the vacation model is a product of two terms, one of which is the generating function for the corresponding system with no vacations, and the other is something that has to do only with the vacations. And it can be shown, although I didn't show it here, but it can be shown that this thing can be written this way. I could call this f v tilde of z. Okay, now what this is, this f is the generating function of these capital P's. This f right over here, that is, when you put this together, this turns out to be the generating function of the number of customers that arrive during a forward recurrence time of a vacation. So in other words, if I looked at a sequence of vacations, a renewal process in which that length is a vacation and that length is a vacation and so on, and if I interrupted that vacation at random and then asked for the distribution function of the forward recurrence time of vacation, and then asked for the number of customers that arrive according to a Poisson process during that forward recurrence time, then its generating function is given by exactly this form in terms of the generating function of the number of customers that arrive during an arbitrary vacation. This is all done in the book, although it's not done in that exercise, but it's not identified as such, although you could do that. And in fact, if you're interested, all of this is summarized in some of the papers that are on my website. In particular, there's a paper called Some Reflections on the Renewal Theory Paradox in Queuing Theory. And if you read that, that'll kind of put all of this together in an intuitive way. All right, my point here is that two things. First of all, or several things. First of all, notice that if this is a generating function and this is a generating function, that since this generating function is the product of generating functions, that means that the number generated by this has the same distribution as the sum of the number generated by this plus the number generated by this. The second point is that this part contains only the probabilities associated with the vacations, and this part contains only the probabilities associated with the queue without vacations. So it separates those things. So that's amazing. Both of those things are amazing facts. Okay, and the third part is that the part that separates out that has to do with the vacations contains in it the forward recurrence time of an interrupted vacation. So we're going to show what the consequences of that are. Okay, so the bottom line here is that when I take, and this is what's done in this exercise, when I take, I can go from this and take derivatives and calculate average values, average waiting time using Little's formula. And so in fact, on page 223, you get this statement right here. The expected value of the waiting time in the model with vacations is equal to the expected value of the waiting time in the corresponding model without vacations. That comes from this G here, and then there's this piece here. And that turns out to be the generating function, second derivative, evaluated at 1, divided by 2 lambda times the generating function, first derivative, evaluated at 1. And this thing right over here, this in fact is the forward recurrence time, average value of the forward recurrence time of an interrupted vacation. So another way I could write this is as follows. I could also write that the expected value of the waiting time in this model is given by rho over 1 minus rho, h double prime of 1 divided by 2 lambda, h prime of 1, plus f double prime of 1 divided by 2 lambda, f single prime of 1. In other words, this term right over here could be written this way, in which the h is the generating function of the number of customers that arrive during a service time, and this term is the generating function, this f is the generating function of the number of customers that arrive during a vacation. So it's very striking that you see the same thing here. And furthermore, as I already showed in class last time, this corresponds to a forward recurrence time. So that means that the average value of the waiting time can be written this way. The average value of the waiting time in the vacation model. Now, this is what you would get in ordinary MG1, so as you already know, we can write it like this. Here's rho over 1 minus rho, and then this part over here is the same thing as E of x over 2, 1 plus the variance of the service times. I'll write that as sigma squared sub x divided by the mean square of the service times. That's that term right there. And this term right over here is the same as that, except that instead of having service times, it has vacation times. So this is the expected value of the vacation time divided by 2 times 1 plus the variance of a vacation time divided by the square of the mean vacation time. Okay, so again, what you see is this decomposition. This is now the mean value decomposition. What it says is that in a queuing model, in an MGM1 queuing model with vacations, the average waiting time decomposes into a sum of two pieces. And one piece is exactly what you would get if there were no vacations, and the other piece just has to do with the vacations. And surprisingly, in both cases, this piece over here corresponds to the forward recurrence time, as we stated earlier. This is an important point. This piece right here, that's the forward recurrence time of a service time, and this piece right over here, that's the forward recurrence time of a vacation time. So the forward recurrence times, that is the interrupted intervals, which have different distributions than ordinary intervals, appears here, as we already saw, and we derived this several different ways, and now because of this term, it appears here as well. Except that in this case, it's the vacation that's interrupted. In this case, it's the service time that's interrupted. Now, the fact that the waiting time can be viewed as the sum of these two pieces does not mean that an individual customer, when he arrives, actually first waits an amount that has to do only with the server when there are no vacations, and the other having to do only with the vacations. That's not what happens. What happens is those two things are combined with each other, because when a customer arrives, if the server is on vacation, well, then he waits for the end of the vacation, but while he's waiting, other customers are arriving as well. So when the vacation ends, then the server starts to work. But the server starts to work with more customers present than he would if there were no vacations. If the customer arrives when the server's working, then he doesn't wait during a vacation, but he feels the effect of the vacations because the other customers who were there during that time, some of them arrived during the preceding vacation. So the vacations, the operation of the vacation model takes the service times and the vacations and kind of puts them together, but when you actually solve the problem, they separate, and that's the stochastic decomposition. And this has some rather strange properties, and so I want to illustrate that and show that bizarre things can happen. Okay, so let's go from here. Oh, and by the way, one thing I wanted to do is I wanted to look at this. This f of z, this represents the generating function of the number of customers that arrived during a vacation. Now, one of the nice things about this is that it represents things in terms of the vacations in terms of how many arrive rather than how long the vacation lasts. Maybe that looks like it's more complicated, but actually it's simpler. For example, suppose that I said that f of z f of z is z to the n. Okay, so what does that mean? That means that since this generates the probabilities that correspond to the number that arrived during a vacation, that means that the probabilities, the coefficients of all of the terms in this expansion are 0 except 1. So that means that the probability that when I return from a vacation, there are n customers present is 1, and all the other probabilities must be 0. Okay, so what does this mean? This means that if I require that whenever I return from a vacation, the number of, or that is whenever, I shouldn't say that. What I should say is, well, yeah, in fact, that's what this says. This says that whenever I return from a vacation, the number of customers present will be exactly n. The only way that can happen is if the vacation is triggered by the arrival of the nth customer during the vacation. Because if somehow or other the arrivals occurred during an interval that was independent of the arrival process, then you couldn't guarantee that when the vacation ended, there would always be exactly n customers there. So by setting f of z equals z to the n, I operate the queue under what's called the n policy, which means that the server goes away for a length of time and it just stays on vacation until the nth customer arrives. And as soon as the nth customer arrives, it's watching and immediately starts work, so that when it returns from a vacation and starts work, it starts with a queue of size n. Now, what that means is that the vacation lengths are not independent of the arrival process. In fact, the arrival process generates them. And exactly how long that takes, well, that would take the time until exactly the nth customer arrived. So this is a very nice way of representing that idea. In particular, suppose that n is equal to 1. If f of z equals z, that means that the probability is 1 that when the vacation ended, there would be exactly one customer present. But that's exactly the same as if there were no vacations. Because if there are no vacations, then what that means is that the server is always available, and as soon as a customer arrives, the server begins to work on it. So it doesn't really matter whether the server is away someplace else and comes back as soon as one customer arrives, or is just sitting there waiting for one customer to arrive. As far as the performance of the queue is concerned, what matters is that as soon as a customer arrives, the server is available to work. So if I took n is equal to 1, then I should get the ordinary vacation model. And if I come down here and set f of z equal to z, you can see that the z minus 1 cancels. F prime of 1 would be 1. The average would be exactly 1. And I would have g hat is equal to g of z, which is exactly what we should get. Okay, so one of the statements that people often make when they discuss vacation models and set up the conditions is they sort of, without thinking about it, say that the vacation lengths must be independent of the arrival process, but that's not required for this. Okay, let's do an example. So I'm going to plug in some numbers here. So I'm going to take MD1, because it's the easiest thing. So I'm going to take constant service times, and I'm going to take the average service time is equal to 1, and I'll take rho equal to 80%. And so what would be the expected value of the waiting time in the vacation model? Well, it would be equal to rho over 1 minus rho times the average service time divided by 2 times 1 plus the variance of the service times divided by the square of the average service time, plus the average value of the length of a vacation divided by 2 times 1 plus the variance of the vacation lengths divided by the square of the average vacation length. So if this were MD1, which is what I have here because I have a 0, then this term over here turns out to be exactly 2. So I get 2 plus this guy. Average vacation length divided by 2, 1 plus sigma squared of the variance divided by the square of the average vacation length. Now, if it were MM1 instead of MD1, in this case, this value would be a 4 because that 0 would be a 1. In fact, this is I believe the one that we did in homework 5 and homework 6. Okay, so this would either be 2 or 4, but this part would not change. So now what I want to do is I want to look at different assumptions about how long the vacation lasts and see what the effect of that is. Okay, so let's look at case number 1. Case number 1, I'm going to take the vacations of length 0. So in other words, I'm taking ordinary MG1, no vacations. Actually, in this case, it's ordinary MD1 because we're looking at the particular case of constant service times. Okay, so what would I get? I would get the average length of a waiting time in the vacation model is 2 plus that. Okay, now, if the vacations are of length 0, that means the average length of a vacation is 0. So this would be 0, and the answer would be 2, which, of course, is exactly what you know. If the vacations are all of length 0, then that means, in effect, that the server is simply going away for no time, so it's looking continually at the system. And so if the vacations are 0, then that's as if there were no vacations. So this is the ordinary MD1 model. All right, suppose that, let's go over here. So let's look at case number 2. Suppose that V equals 1. In other words, I'm going to choose constant vacation times and each vacation has the same length as a service time. Same as service time. Okay, so according to our formula, the average waiting time now would be equal to the original 2 plus the forward recurrence time of a vacation. In this case, it's easy to see what that is. Well, first let me write out the formula. I would get 1/2 times 1 plus. Now, we have constant vacations of length 1, so that's the average vacation length, that 1. And then the variance of the vacation length would be 0. The denominator would be this 1 squared, and so we would get 2 plus 1/2, or 2.5. But that's not surprising now if I remember that the formula says that the additional part that I add on to the case without vacations is the forward recurrence time of a vacation. So if a vacation has a constant length 1, then if I interrupt the vacation at random, the average remainder of the vacation would be 1/2. That's the simplest case. You don't need any formulas for that. In fact, the only time that the average length of an interrupted interval is half the length of the interval is the case where the intervals are constant. Okay, so the effect of a vacation whose length is 1 unit is to increase the average waiting time by 1/2 a unit. Okay, so case number 3. Suppose that the vacations are all of length 2. So then the average waiting time would be the same 2, plus now it would be 2 over 2 times 1 plus 0 over 2 squared. This value turns out to be equal to 1, and the answer would be 3. But once again, that makes sense because what it says is that, on the one hand, if the vacation length is 2 and it's a constant, that means that the average length of an interrupted vacation would be of length 1. So I would add that to the original 2, and 2 plus 1 is equal to 3. And once again, I see that each constant vacation increases the overall average waiting time by 1/2 a unit. So when the vacation was 1 unit, then this was 2 plus 1/2. And when it's 2 units, it's 2 plus 1. Okay, case number 4. Now I'm going to take that the vacation length is equal to a random variable y, where y is as defined in homework 2. So you remember in homework 2 we had that renewal theory problem in which the renewal intervals were random, and what we defined is this: the probability that y is equal to 1 was equal to 9.9, and the probability that y is equal to 11 was 0.1. And from that, we calculated the average value of y, and so it turned out to be 1 times 0.9 plus 11 times 0.1, and that, of course, is exactly 2. Okay, so now the average length of a vacation is 2, just as it is in case 3. But the variance, of course, is different, and so we have this. Sigma squared sub y, the variance of this random variable y, is equal to, well, remember that the variance is equal to the second moment minus the square of the first moment. So to get the second moment, I would take 1 squared times 0.9 plus 11 squared times 0.1. That's the second moment. And then I would subtract the first moment squared. The first moment was 2, so I subtract 2 squared. And by arithmetic, that gives me the value 9. Okay, so let's go over to here. Okay, so now the average value of the waiting time in the vacation model is equal to the original 2, if there were no vacations, plus 2, which is the average length of the vacation, divided by 2 times 1 plus the variance of the vacations, which is 9, divided by the square of the average, which is 4, and arithmetic gives me 5.25. So the difference between case number 3 and case number 4 is simply the variability in the vacations, and that increases the average waiting time from 3 to 5.25. Okay, now case number 5. Now what I'm going to do is I'm going to take the vacation length as equal to y plus 1. In other words, to each vacation, I'm going to add a service time. Add 1 service time. So we're going to slow things down. We're going to send the server away on vacation, and the vacations are going to be just like they were in example number 4, except that when I get done, instead of starting to work, I'm going to just wait 1 more service time. And 1 more service time, as we saw before, has the effect of increasing the overall vacation, the overall waiting time by an amount equal to 1/2. So you would expect that this would produce longer waiting times. Okay, so let's plug it in. So what we get is that the average value of the waiting time in this vacation model is equal to the 2, that's what you get if there were no vacations, plus the first term is the expected value of the vacation length, which is the original 2 plus the 1, because I just added on 1 constant service time to the vacation. So that's going to give me 2 plus 1 divided by 2. Then I have 1 plus. The denominator here is the square of the average vacation length. That would be 2 plus 1 squared. And the numerator is the variance of the vacation length. Now the variance before was 9, Now I'm adding a term, but the term I'm adding is a constant. So when I add on the constant, that doesn't change the variability. So the new variance is the sum 9 plus 0. In other words, it's the same as it was before. And now I do this arithmetic, and this arithmetic is straightforward, and the answer turns out to be 5. So what happened? Every place so far, I increased the vacations by a constant value 1, and that increases the overall waiting time by an average amount of 0.25. That is a quarter of a service time. But now I increase the average vacation length. I increase the vacation length exactly by 1. So in other words, I'm going to add in that same constant amount equal to a service time in the vacation, and the average length of the vacation, of the waiting time drops. Instead of adding a half, it drops by a quarter. The average waiting time in the model where I force the server to sit around and do nothing is less than it is if I serve as fast as possible. So that's pretty bizarre. But in fact, I've simulated this. Of course, there's no doubt there's no need to simulate it. And of course, it's right. And this is exactly the same effect that you saw in homework 2, where if you remember, you used exactly the same example. And what we did is we increased the lengths of the intervals that were interrupted, and then we showed that as the length of the interval got larger, the amount of the value of the interrupted interval actually got smaller. Okay, so here it is, exactly the same effect, but now it's in a much more stark perspective, because what we see is every time we add a constant amount to the vacation, which is the amount that the server's away doing something else, we increase the amount of the waiting time by half a unit, unless we have this variable vacation length. And in this particular case, when I increase the vacation length by an amount exactly equal to 1 unit, the average waiting time, instead of rising by a half, drops by a quarter. So it's better for the server to, when it comes back from vacation, whether there's work waiting to be done or not, it's better for the server to go away and take a smoke or drink a cup of coffee and come back 1 unit later and then serve, even though customers may be queuing up, because the end result is that the average waiting time will be less if you force the server to be idle than if you don't. Now, in the model in which we have cyclic queues or polling, we have something like this. Here are the stations, and what happens is the server serves a station, and then it switches to the next station, and so on. And the way this is analyzed is to treat one of the queues, any one of them, as a target queue, and imagine that when you're serving the other queues, you're on vacation. And then what you do is you determine, although it's complicated, you determine the generating function of the number of customers that are waiting here when you return based on what's going on in the other queues. And you have this decomposition, and that's what allows you to solve the problem, because you separate out the pieces. Okay, now, what this means is that depending on what's going on here, it's possible that spending more time cycling around actually reduces the waiting times at the queues. In fact, it's conceivable that I could force the server to be idle. And one of the papers that I'm asking you to take a look at actually makes this point. I could take a system like this, and I could force the server to be idle, just like I do here, by inserting a time during which I just hold the server out whether there's work to be done or not. So more work is building up, but the end result is that the total length of time it takes to go around and serve everybody is less. Now, this was actually discovered sort of empirically. I'm not sure exactly to what extent this is useful in actually modeling systems like this, and to what extent it's just suggestive. But in manufacturing engineering, this is a standard kind of model, because here the idea is you have a server, and the server's doing some work. And when it's done with that work, it switches to some other station and it does some other work. And then it switches to some other station and does some other work. And in switching, there's some time that it takes to switch from here to here, or to set up. It may be that this is a machine, and once it's done doing this particular operation, you set things up, and then it does this particular operation. So in manufacturing engineering, these are important models. So what was observed was that it was that it's sort of obvious that if you want to improve things, you want to take the setup time or the switchover time, and you want to minimize it. So you want to make the server go faster from here to here, or set up faster, because while it's walking or switching or setting up, time is being wasted because jobs are arriving just as before. And what was found was that when you improve things by making the server switch faster or set up faster, the actual waiting times increase. Things get worse. Okay? Why do they get worse? Well, it's exactly the reverse of this effect. Here we showed that by forcing the server to be idle, that is forcing the server to work more slowly, I can make the waiting times less. So therefore, by forcing the server to work faster, I would make the waiting times worse. So in fact, people observed this, but they couldn't explain it. It didn't seem to make any sense. And then a series of papers were written, one of which is one of the ones I'm mentioning here, which explains that the reason for this is because of this forward recurrence time effect. That is, because of the variabilities of what's going on during the vacation. And if by making the server work slower, you can minimize the waiting times. Therefore, by making the server work faster, you might be maximizing the waiting times or making them larger. Now, the actual numerical amount is probably not much, so if you measured it, it would probably be lost in noise. But nevertheless, this gives important insights into the way these things work. Now, another interesting version of this is, getting back to the polling model, is that in the original model that was analyzed, this original polling model in 1970, the assumption was made that the length of time it takes to switch from one station to the next is 0. That's a standard kind of assumption you would make because, for example, in ordinary MG1, you assume that it doesn't take any time for a customer to move from the queue to the server once the server is ready for it. So one argument, one model is that the length of time it takes to go from here to here to switch is 0. And another argument is, well, let's introduce some random variable that corresponds to the length of time it takes to switch. Could be a constant, could be variable, depending on the particular model. Now, surprisingly, it turns out, if you think about it, that the case in which the switchover time is 0 is more complicated to analyze than the case in which it's not. Because the typical way to look at something like this is not to represent things in terms of generating functions, as I've said, but rather to represent things in terms of times it takes. And as I say, that turns out to be somewhat misleading. Now, if I represent everything in terms of the times it takes to switch from one place to another, I have to recognize that if the switchover times are 0, the length of time it takes to make a cycle when there's nobody waiting is 0, which means that if ever the server leaves a station empty and there's no one waiting in the other stations, then the server is going to make an infinite number of switches until somebody arrives. And when you do the analysis and you count in that infinite number, everything screws up because you get your total time spent in a cycle is dominated by the time that you spend doing nothing, because you're going to make an infinite number of switches in any finite and infinite number of cycles in any time in which the system is idle. So when people studied this model for the case in which the switchover times were not 0, that was conceptually easier, but it gave a more complicated analysis. What was discovered was that what we discovered, that's why I'm stating it here, is that if I don't analyze this from the viewpoint of the time it takes to go around, the cycle time, but rather the number of customers, the generating functions, then it turns out that when you write the solution for the complicated case, it turns out that the answer factors into two pieces. That is, there's a decomposition. One piece describes a corresponding model in which the switchover times are 0, and the other piece has to do only with the switchover times and the forward recurrence times of the switchover times. So once again, you get this separation. What that means is that if I want to analyze a model in which the switchover times of any particular distribution, all I need to do is analyze the model for the case in which the switchover times are 0, for which the analysis is, relatively speaking, simple, and then add on the effect of the switchover times, rather than recognizing, or rather, that is, just like in the vacation model, what happens is you have this stochastic decomposition, in which even though in the actual application of the model everything is intertwined, in the formula that results from the analysis, the part that corresponds to the switchover times and the part that corresponds to the model if there were no switchover times just breaks into two pieces, and you can analyze each one by itself, which makes things much simpler. So if you look at the website, that is my home page, it has some selected publications. And let me read the titles of the ones that I posted. Okay, going backwards in chronological order, the first two are the 1969 and 1970 papers on Q served in cyclic orders, that's the polling model, and the vacation model. And then in 85, there's the paper with Furman, stochastic decompositions in the MG1Q with generalized vacations. And that's the one that handles this stuff in general for the vacation model, not just for exhaustive service. And then there's a paper by Srinivasan, New, and myself in 1995 titled Relating Polling Models with Zero and Non-Zero Switchover Times. And that relates to this particular case right here. It shows that the case in which the switchover times are non-zero can be obtained from the case where the switchover times are 0 by simply adding on a term, which is very simple. Then in another paper, which actually is clearer in my opinion, but not as general, this one is by myself, Shunchen Nu, and Srinivasan. There's a series of papers here by the three of us, and we worked together on these polling models. We had a joint NSF grant, and these were our results. And this one is titled, A Decomposition Theorem for Polling Models. The switchover times are effectively additive. And effectively additive, that's the idea that when you analyze the thing with the switchover times, the end result is just as if you took the result out, just like over here, and took the same model, even though it's complicated, but without switchover times, and added in a piece. This is effectively additive, and the piece that's added in here has something to do only with the switchover times and not with the service times. Then there's a paper called Some Reflections on the Renewal Theory Paradox in Queuing Theory, and that's more of a philosophical kind of musing about how this forward recurrence time things keeps appearing all over the place, and how it has these strange effects, and why it appears. And of course, to say that it appears because when you do the analysis it drops out, well, that's true, but that's not really helpful in an intuitive sense. And so what you like to do is, once you know what the answer is, maybe you can go backwards and explain why it turns out that way. So for example, when I derived the formula for waiting times in MG1, the Polachek-Hinchin mean waiting time formula, I was able to give a simple argument that gave me the answer with those the forward recurrence time term But that was because I already knew what the answer was going to be. And if I didn't know that, I don't think I would have relied on that result, even though it was very simple. There's a paper called, and I'll get back to this one about the renewal theory paradox in a moment. There's a paper called, also by myself, New and Srinivasan, Setups in Polling Models. Does it make sense to set up if no work is waiting? Now, a setup, if you're looking at the manufacturing context, what happens is that when you get to a station and you're going to do some work there, then often you have to adjust the machinery. You have to set it up so that it can now handle the new job. So that's sort of like a switchover time. And the question here is, yeah, but if it's a setup, that means that you have a choice, because you could simply look and see, is work waiting to be done? If work isn't waiting to be done, then what I would do is I would not bother to set up, because what's the point? Nothing's waiting. I might as well go on to the next queue. Now, it turns out that in some cases, and we were able to get some really nice formulas for this, in some cases, even though there's no work waiting, it's better to set up. That's in a sense like introducing an extra piece of a vacation. So you force the system to set up even though there's no work to be done, and the end result is that while you're setting up, you might be lucky and some work will arrive, and you'll already be ready for it, and the end result will be that you will minimize the waiting times for the whole system. In other words, this gives conditions under which it's better to set up as if work is going to arrive, even though there's no work there, rather than simply going on and doing work that's already there and that you know needs to be taken care of. So again, it's this. It turns out that this forward recurrence time result drops out, and that has these strange effects. Okay, let me go back and just state something more generally here about these vacation models. Any questions about this? There's a lot of stuff here, and there's a lot of different variations, so that's why zillions of papers have been written. But some of these papers, most of these papers, look very difficult because there's a lot of algebra, and the trick is to be able to see through that so you know where you're going and can get to and either explain the answer or get to the answer that you might not have been able to get to if you weren't guided somehow by some feeling about what might happen. All right, so if you're interested in these things, I suggest take a look at these papers. If people are interested in writing a thesis or doing independent study or something like that, this stuff is a natural. And one of the nice advantages is that, at least up until about 95 or so, maybe later, Takagi was continually updating his bibliography and his survey that explained what the state of the art was. So a lot of work is done for you rather than having to search through the literature. Okay, now, in the vacation model, we saw that the generating function for the number of customers in the vacation model, that's what the hat stands for, was given by this product, f of z minus 1 divided by f prime of 1, z minus 1, g of z. And this is on page 223 in the textbook. And this is the one that says that the generating function is a product of things, this being the generating function for the case in which there are no vacations, and this, it turns out, being the generating function for the number that arrive during a forward recurrence time of a vacation. Okay, so I can write that this way. I'll call it f of z sub tilde, v sub tilde. Okay, the v stands for vacations, and the tilde means forward recurrence time. Now, it's a short step, actually, to go from that to this statement. Omega hat of s is equal to omega of s times phi of s sub v tilde. What this says is that the Laplace-Dirichlet transform of the distribution function of waiting times in the FIFO vacation model is the product of two transforms, one of which is the Laplace-Dirichlet transform for the case without vacations, which we've already derived, and the other of which is the Laplace dilutive transform of the forward recurrence time of a vacation. So now we're translating in the vacation model, just like we did in the ordinary MG1 model, from the generating function to the waiting time. This is the Laplace dilutive transform of the waiting time. So what that says is that since this is a transform and that's a transform, that means that this is the transform of a random variable that looks like a sum of independent random variables. In other words, another way to write it is this. If I were to take the inverse of this, I would get W tilde. This is the waiting time. This is the random variable for the waiting time in the vacation model. And then you write an equal sign with a little d. And the d means is distributed as the waiting time if there were no vacations plus another random piece, which is a forward recurrence time of a vacation. So the interesting part there, this is the stochastic decomposition, and this is what's done in the 1985 paper with Furman. It's done even more generally there. But what this says is that, interestingly, not that the waiting time in the vacation model is a sum of a waiting time if there were no vacations plus a forward recurrence time for an individual customer. That is, it's not true that an individual customer waits that and then that, or vice versa. What's true is that, statistically speaking, in distribution, this is just as if you took a random variable that corresponds to what you would wait if there were no vacations, a random variable that corresponds to the value of an interrupted vacation time, and added them together statistically, probabilistically, it would be the same thing. Which means that if I wanted to find the distribution function, let's say, if I wanted to find the probability in a vacation model that the waiting time lay in certain interval, I could do that by finding the distribution of waiting times if there were no vacations, the distribution of the forward recurrence time, and taking the convolution of those two distributions, and then calculating the probabilities from that convolution, even though an individual customer does not wait that time plus that time. I would still get the right answer. And that means that in some cases, I can actually do this. For example, suppose that the original Q has exponential service times. In fact, that's the only simple case in which I actually know what this is. We know how to calculate the distribution function of waiting times in the ordinary MM1Q. And then I could just say, well, now suppose the vacation times, for example, were exponential. Then I would take the convolution of that with an exponential. Of course, the exponential, in that case, the interrupted vacation and the full vacation have this, and an ordinary vacation have the same distribution. Suppose that the vacations were constant. Then an interrupted vacation would be uniform. And so I could take the convolution of this, which is sort of like an exponential, with a uniform and get an answer. And it turns out, that, of course, that that's the right answer. And in the past, I've given a homework problem in which I asked people to do this and compare this with simulation, and it all works out. Fortunately for you, I went slower this time than I've gone in the past, and so we didn't get to this problem. But in the past, that was the final exam. And in this case, the last two times I taught the course, I didn't actually use that because I didn't feel that we had gone far enough to do it. But about 3 years ago, I actually used this problem, and it worked out beautifully. Of course, it had to, but nevertheless, I thought it was really neat. And what it required from the simulation point of view was you had to take the simulation for ordinary MG1, which you already have, and then add in the vacations. So that changed the simulation slightly, and compare that with what the theory predicts, and it all worked out. Okay, any questions about that? Now, there's one last thing I'd like to show, which I think is kind of interesting. We know that for MG1 FIFO, if we have FIFO, then I know that the average waiting time, I'll call it EW sub F for FIFO. This is the Pollaczek-Hinchon formula. Rho over 1 minus rho, average service time over 2, 1 plus the variance of the service times divided by the square of the average service time. All right, so we already know that. And of course, this is the forward recurrence time result right here. Now, suppose I had LIFO. Actually, LIFO preemptive resume. And here's what LIFO preemptive resume means. LIFO preemptive resume, what happens is, instead of when a customer arrives joining the end of the queue, now what happens when a customer arrives is he goes into service immediately. When he goes into service immediately, if somebody's already in service, then that customer is bumped out and everybody is moved back one. So it's LIFO because it's last in, first out. And it's preemptive resume. What that means is that whenever a customer who's been bumped re-enters the server, he continues his service from where he left off. So the total amount of work that's done is exactly the same in both cases. So they have the same utilization. And the question you want to ask is, if I'm the administrator of such a system, is it better or worse for me to operate under LIFO as opposed to FIFO? In other words, I could look at it like this. Here is the average waiting time under FIFO, and here's the average waiting time under LIFO. Now, of course, if this server is like at the bakery counter at Publix, then you can't have somebody coming in and bumping somebody else out or you have a riot. But if these are messages, then they don't know whether they're bumped in or out, and so therefore it's up to the administrator to decide, well, which way it's going to work better. Because the messages don't know when they arrived or care how long they wait. All you care about is, on average, how do you get the messages out as fast as possible. So one possibility is that FIFO is better than LIFO. In other words, the average waiting time for FIFO is less than LIFO. Another is that LIFO is better than FIFO. A third possibility is that LIFO and FIFO are actually the same. Okay, now, why should we have any of these? From the viewpoint of the benefit of using LIFO is that when a customer arrives, he gets service immediately. And if his service time is short, then he's not likely to be interrupted. So from the viewpoint of customers whose service requirement is short, they get in and out very quickly. And so maybe this makes things overall work better. On the other hand, if a customer gets bumped, then he's going to go back in the queue, and the customer who bumped him might himself get bumped, and he's going to move back in the queue. And so it's likely that if you have a long service time, you're more likely to be bumped, and then if you are bumped, you're likely to have even a greater waiting time. And so the result is that customers whose service requirement is short are going to get out faster, but customers whose service requirement is long are going to get out slower, so they might just exactly balance because the total amount of work done is the same, so they might be equal. So the question is, well, we could vote on this, although there really isn't enough of a sample here to make a vote, but here are the three possibilities. And then when I present this, I often say, okay, now, there's a fourth possibility here, which people tend not to think of, and that is, well, maybe it depends. And if it depends on anything, what it's going to depend on is it's going to depend on the distribution of service times, because that's the only difference between them in terms of the assumptions, because the assumptions of the LIFO and FIFO are that you have Poisson input, that since we can't compare apples and oranges, we're going to look at the case where the utilization is the same, and just say, okay, now for this system, should we operate under FIFO? Should we operate under LIFO? And the answer is, well, maybe it depends on what the service time distribution is, and that comes into play right over here in this forward recurrence time term. So what we really need to know is, what's the formula for the average waiting time under LIFO? Now, LIFO seems a lot more complicated than FIFO. In fact, it's more complicated to analyze, but amazingly, it turns out that the answer is simpler. It turns out that if I have LIFO, preemptive resume, the answer is given by this. In other words, you have here a service time instead of a forward recurrence time of a service time. Okay, so what I'm really doing then, I'm asking is I want to compare this formula against this formula and see which one produces a smaller average waiting time. But before we do that, there's something rather remarkable about this, and that is that there's no variance term in here. So in this case, the average waiting time is insensitive to the service time distribution, because the only thing that affects it is the utilization and the average service time. So that means that over here, different service time distributions are going to have an effect depending on how variable they are, but over here they have no effect. So that's really amazing. And in fact, it turns out that if you compare this and this, what this says is that, well, there's obviously a relationship between the two, which is that this one is the same as this one multiplied by this term over here. So why is that? And a sort of a semi-answer is given in the paper that's called Some Reflections, because the point of that paper is to look at various different cases where you have this forward recurrence time term and why it arises, other than to say, well, it just comes out of the algebra. Okay, so let's plot. Let's see what the answer is. So what I'm going to do here is I'm going to draw a graph of the average waiting time as a function of the variance of the service times, because that's the only thing that differs between the two. Okay, now suppose that I have LIFO. If I have LIFO, the average waiting time does not depend on the variance. So whatever the parameters are, I'm just going to get a straight line like this. So this is the average waiting time under LIFO. Okay, now let's compare this with the graph for FIFO. Well, we're going to plot against the variance. So suppose the variance is 0. If the variance is 0, that means that we have constant service time, and all that means is that this multiplying term is 1, so this formula gives me the same as this formula divided by 2. So if the variance is 0, then here is the average waiting time under FIFO. So FIFO is better than LIFO here because its average waiting time is only half as much. But now as the variance gets bigger, the average waiting time grows linearly because the variance is a linear function there. So the curve would look like that. So there's a critical value right here, such that if the variance is less than this critical value, then FIFO is better. But if the variance is more, then LIFO is better. Okay, so what is that critical value? And the answer is, well, it's easy to check that these two curves are going to be exactly equal when the variance is equal to the mean square. Because in that case, this ratio will be 1, that'll be 2, that'll cancel that 2, and that'll give me exactly this formula here. So in other words, the critical point is when the variance is equal to the square of the average. But when the variance is equal to the square of the average, that's when the service times are exponential. And the exponential is the case when there's no memory, and so the forward recurrence time stuff by the Markov property just says that, well, the past is irrelevant. So this is a rather surprising and enlightening result, And it's just another example of how all of these things interact and how they give you not only formulas, but insight. And as I say, it's the insight, the intuition, or the counterintuition that makes this whole subject interesting. Okay, so I guess it sort of sums up what I wanted to say today. And we have just a couple minutes left. So does anybody have any questions or comments or anything at the moment? Nobody can think of our shill student over here who asked the questions is not here today, so no questions. Okay, so that's the end of the course, and I enjoyed it. I hope you did. And if you're interested in any of this stuff for independent study or something like that, come back and see me and we can talk. Okay, homework 6 is due for the live class. It's due on May 5th, although earlier would be better. May 5th is the end of the semester. I think it's a Friday, and then grades are due the following Monday. For people who are taking it off-site, the due date is May 17th, so that you have 2 more weeks. Now, in either case, if for some reason you can't get your work done by that time, then I'm willing to give an I if you ask for it. So what that means is you send me an email saying that you want to get an I and give me a reason. Obviously, the reason is that you don't have enough time to do it, and saying exactly what your schedule is. So say that I'm going to get this done by such and such a date, and then I have to fill out a form, which you have to sign, saying that if you don't hand in your homework by this date, then the grade will revert to something, which I have to state, and otherwise, then the grade is whatever it is based on what you hand in. So if you want an incomplete, you have to ask for it, and then you have to sign a form, and when you ask for it, you have to give some kind of excuse, which I write on the form, and you have to say the date by which you're going to get your work done. And otherwise, the answer is hand it in by May 5th. Okay? Okay, any other questions? Comments? Okay. So long. You too.